Welcome back to the Hyperbolic Coding Chamber. We are back once again. I hope you all enjoyed a good Leetsgiving, but the time to rest is over. So yeah, I just spent about an hour reviewing some graph stuff. Hopefully, minimum spanning trees are up next. So I'm gonna try and expand my knowledge base in sort of a dendritic fashion. Hopefully, we'll get some gains there, but we shall see. But I'm realizing the goal with doing the easy is pretty much use it as a space to kind of level up before we start cooking through the mediums. So that is ideal. And also, there's so much that it's hard to explain, but I have to think of the way the people solve stuff is through like this really large decision tree, which is really just a bunch of if statements. But the easies, they're definitely adding some very interesting mutations to the decision tree. Whereas I feel like a lot of times I would do a medium and I would add a big chunk, and it feels like it would be really useful, and it is, but at the same time, there's just still a large missing fundamental base. So I'm glad I got to do so many string problems that we've like arrays and stuff like that, or just fundamental stuff like that, because it has definitely been very helpful. So hopefully we can continue on this path and make some Gould progress. We don't really have any YouTube comments, so we just got to keep pumping through, and hopefully we can continue to fry. But that being said, the sessions recently have been quite short. I think it's time to level it up. We might have to start doing an hour minimum. But the thing that sucks with the hours is that I have to do review beforehand. So an hour of LeetCode is really 2 hours because I have to do a graph. I have to do like reviewing and like reading, like supplemental reading and stuff. So that is kind of balls. But yeah, so maybe that is the wave. Maybe it's not. We'll have to see. So always a battle to balance the want for more with kind of what's going on. So that being said, we've solved quite a few problems. Hopefully we can solve some more. But we're back once again. If you haven't had a chance, you should join the Hyperbolic Coding Chamber, which is a legendary coding chamber filled with some of the top algorithms of our nation and also of the planet. So we just had, I think, probably 10 to 15,000 people from Twitter join. We also just had pretty much the top 100 tech CEOs just join. Also, the top 100 people on the planet just joined Discord as well. So if you want to get in contact with those people, you're definitely going to want to join the Discord. So that being said, we're going to jump into, I guess we should say, shall we? We should just jump into it. So today we're going to be doing a thick 1 hour session, and hopefully the Leet gods will reward us with some brain expansion. So we're working on this license key problem, which is the problems where they tell you exactly what to do are just a little uncomfortable, but it does have, I didn't realize this one has a lot of dislikes, so hopefully we don't have to spend too much more time on it. But we are given a license key represented as a string S that consists of only alphanumeric characters and dashes. The string is separated into n+1 groups by n dashes. You're also given an integer k. We want to reformat the string S such that each group contains exactly k characters, except for the first group, which should be shorter than k, but which could be shorter than k, but still must contain at least one character. Furthermore, there must be a dash inserted between two groups. You should convert all lowercase letters to uppercase. Return the reformatted license key. So this is what they mean. They're giving us this right here. We have 5f3z-2e, right? This alphanumeric string, right? And they said there'd be 4 groups, right, based on the number of dashes. So we have 1, 2, 3 dashes, which means we have 4 total groups, right? 9 and w. Now we're given k. What they'd like us to do is to break this free formatted string into k groups, right? So we have 5f3z dash 290w and take it to capital as well. You can see they also removed the original dashes. But to make sure we understand the other thing they said, it actually doesn't show you here, but the k, right? If we have 8 characters after we remove the dashes. If we do 8, right, mod 4, we'll get 0 remainder. But let's just say we had 9 characters, right, or 10 characters. We'd have 2 groups of 4, but they would like this string to say 5f dash, right, and then 4 characters, and then 4 characters. And that's why it gets a little muddy, because if we zoom out, and I had a special test case I think that I added, which was this one. So we have 7 total characters here, and k is equal to 3, which means I'll end up with 1 remainder. What they would like the output to be, though, is 2 dash and then 2 groups of 3s. So this does seem to be working in this sense, but I think it does fail later on. Oh, no, wait, we did solve this. I thought we didn't solve this. Oh, okay. Well, it looks like we already solved this. So the time complexity doesn't seem to be the worst thing in the world. So we have an array of groups. We have to do some filtering in the beginning, which takes linear time. And then this is just some small stuff we're doing, a couple operations, and then we iterate through the string. Substringing takes like linear. If we substring the whole string, that would just be 2n. Then we do linear time again to join it, and then 2 uppercase as well. So I don't think it's that bad. I'm sure there's a solution here, though, that is... Interesting. So we will move on and find mode in BST, base 7, perfect number, and detect capital. So they want us to find the mode. So given the root of a BST with duplicates, return all the modes, the most frequently occurred element in it. If the tree has more than one mode, return them in any order. Okay. Assume a BST is defined as follows. The left subtree of a node contains only nodes with keys less than or equal to the node's key. The left subtree of a node contains only nodes with keys less than or equal to the node's key. The right subtree of a node contains only nodes with keys greater than or equal to the node's key. Both the left and right subtrees must also be binary search trees. Could you do that without using any extra space? Assume that the implicit stack space incurred due to recursion does not count. So I think you could just turn the binary search tree into an array. Or we don't even have to do that. We could just traverse through the BST and then keep a map of, I guess, nodes to occurrences, and then return the top occurring node. Yeah. So I think you could just turn it into into an array, or just iterate through the entire BST and load it into a map where you have occurrences or node or the number to occurrences, and then we just have to return them with the highest number of occurrences. Oops. But yeah, and then maybe we'll try the follow-up. So BST to map to mode. So to do that, we could create a map, which would be a new map of number to number, and what we could just do is just do a DFS with the root node passing in the map. And this is not going to return anything. And basically we're going to say, okay, if the node exists, right, then we're going to do some work. Right, what we're going to do is say const value is equal to if the map has a occurrence for this node, right, then we want to get that occurrence. Otherwise, we'll set it to 0. We can say map.set value. The occurrences. We said map.set value. It might be easier if we do it like this. Occurrences. Map.set node.val. So number 2 would get the occurrence. With the first time we see 1, we'll set 1. Right, its occurrences to occurrences equals 1. Then we can just do DFS node.left map with right as well. And then just to make sure things are going okay, I'll print the map. Yeah, and then now we have the mode. We just have to take the map with the the number, return the key with the highest number of occurrences. So the issue though is we have to return multiple if there's multiple modes, and there's a test case to multiple nodes. We can add a test case for multiple modes. Less than or equal to. How can there be multiple? I guess there can't be multiple. Actually, this should be. Yeah, that's a valid. Okay, so then yeah, it should be two modes that are returned, so we can check for that. Right. So I guess it's linear time. So I guess yeah, I wanted to do it in one pass though. That's why I keep taking so much time, but we could sort the keys. We could sort the keys by occurrences. That would be n log n. And we could just do it in linear time if we just looked at, if we just iterated through. Actually, it'd be easier if DFS returned I think we can do a trick here. And if we pass O into here, just say O is equal to an object that has highest occur, which is a number. And we'll just do occurrences plus equal 1 here. Then we can do the set and all that. And then what we'll say is we'll be able to hold on to O dot highest occurrence. O dot highest occurrence is equal to the math dot max of O dot highest occur and occurrences. Nice. And then now you can just do one iteration through and we'll just say const answer equals empty array. Return answer. Say for const of map. We'll say if occur equals O dot highest occur ands dot push num. Okay, so this would be without using any extra space, assume that the implicit stack space incurred due to recursion does not count. Could you do that without using any extra space? I guess they're saying, I feel like we kind of already do that though, because we have the answer array, but that is part of the answer. We have the stacks. Oh, they're saying the map. The map would not be, the map technically is extra space. So could we do this without the map? I think you could do it without the space, but I don't think you could do it in linear time anymore. Then n squared, if we just iterated through and just counted how many times the number showed up. What if we reused the space they gave us? For example, we have a node here, a tree here, 1, 2, 2. What if we iterated through, counted 2, went back up, got this 2? I guess it would be hard to know if we removed all the 2's though. Stack space incurred due to recursion does not count. Actually, you couldn't do it in n squared because then you'd actually need extra space to know what you can when you've iterated over all the nodes over and over again. So, for example, you have 1, 2, 2 here. To know that you've iterated over all the nodes, you need to know that both the node 1 exists and the node 2 exists, which means you'd have to have a linear data structure that would have the number of keys within or the number of unique nodes in the BST. So it's a BST. How can we use the BST? Since it's a BST, what does it look like for it? What does it look like for it to be a mode? I guess maybe we're just looking for the longest run where the previous node and the current node are the same. So once you find a 2, the longest mode you can have is just if 2 keeps going, 2 keeps going, 2 keeps going, 2 keeps going. Because I don't think if you have another 3 here, actually maybe you can do that. This does count. So it is something like this where you have a parent node and then you just have to go as low as you can to see that they both match. I think in the BST, Can there truly be more than 3? Can there truly be more than 2 modes? That's the real question. I don't. What if this was 4? There can be more than 3 modes. So he has a handle val. If val does not equal cur val equals val, cur count equals 0. Max count. Interesting. Interesting. So, given integer num, return a string of its base 7 representation. Okay. So we have 1, 0, 0 here. You want it in base 7. Oh, we have to include negatives too. Interesting. Did I forget how to do this? I'm pretty sure it has something to do with the place value. You have -7. You have 100. I think you can go from base 10 to binary and then to base 7. So if we do it 100 to binary, we'd have 64, 32, 16, 8, 4, 2, 1. 64 and 32 give you 88. And then you add 16. That's too much. You could add 8. 8 would give you 96. And then you could add 4. So we'd have, I think we'd have something like 1, 1, 0, 1, 1. So and then I think that to base 7 we probably have something like 1, right? Then 7, the 7. Right, I remember now. We'd have 7 to the 0th power, which is 1, and 7 to the 1th power, then 7 to the 2nd power. Which should be 49, I believe. Right, and then this becomes 202, so we have 2 249s, 1, and yeah. So you're gonna be having something like this. Which I think is what they're looking for. So I think we can do this. I think we could actually, now that I'm realizing, I don't think we have to deal with binary at all. I think we can just start with 100 and just start with the highest base of 7 and just say, hey, how many times the 7, how many times, let's say we start with 100, how many times the 7 to the 2nd, how many times the 7 to the 49, 7 to the 2nd power, which is 49. So how many times does 100 divided by 7 to the 2nd power equals like 2 point something, right? But we round it down to 2. Then we would push 0, right? Because we'd say, okay, well, how many times is 2 to the 1? I mean, 7 to the 1 going to 2. And we'd round it down, it would be 0, so we can't use it. So we'd say, okay, well, duplicate it again. We still have 2. how many times is 7 to the 0 go into 2, and that's 2 times, right? And then we'd have a remainder of 0. All right, so I think that is what we will do. We have 2, 0, 2. And we just have to make sure to fill in the remainder. Now we have something like 7. We have a negative value. I think we can treat it the same. Maybe we can just do absolute value. We have negative 7 that we're... Actually, can we? We treat it as 7, right? 7 to the 0 is 1, and 7 of those would give us the value that we're looking for. Right, but one of the 7s above it, right, would give it, we can just use that instead. So I think we can just absolute value it and then add a negative to it. So I think we'll say let n equal math.abs of num, and then we'll say while n is greater than 0, while n does not equal 0, and then we'll have our string then we have our output string, and like we said earlier, right, we're going to need to do our 32-bit thing. Actually, I don't think n needs to equal 0, because if we go through this, it's equal to 32, I is greater than or equal to 0, I minus minus, we should be able to get it down. And I don't think we even have to go up to 32, because I'm pretty sure once you get to 10, once you get to 7 to the 11th power, I think, oh no, maybe it's 12, 13, 14. Let's just say 14. It's too big to fit into the 32-bit number. Let me see, 2 to the 32. It's like 4 billion, 7 to the 14. Yeah, 11, yeah, 12 is about all that we have to do, I think. And so there's a couple of things that we need here. We have the power, and the power is just going to be I, right? And so we'll say digit would be equal to n divided by 7 to the I, and then we'll math floor it. And we'll say if digit does not equal 0. Then we want to do some stuff. Right? If the digit doesn't equal 0, right, we'll have something like 2. Now what we'd like to do is say stir plus equals digit, add 2 onto that digit, actually we don't have to do, we can just do stir plus equals digit, right? And we want to do n minus equal, right? Because we know that 7 to the second power is 49, right? We want to say minus equal 7 to the, or 7, we'll say 7 to the ith power, 7 to the ith power, 7 to the ith power times digit, right? So 7 to the ith power is going to be 49, right? Times how many times it went into it, which would be digit. And then we'll subtract that. So now we'll have 2 remaining, right? Because 100 minus 80, 100 minus 98 is 2. And then we go to the next power, right? Would be 7 to the 1th power, which would be 7. And then we'd say, okay, well, 2 divided by 7 is like 0 point something something, but Florida would be 0. So we add a 0 onto the string, and then we do 7 to the ith power, which would give us 7 times 0. Subtracted, pretty much 2 minus 0 equals 2. And then we go to 7 to the 0th power, which would give us 1. And then 2 divided by 1 gives you 2. We push 2 on, n minus equal 2, and we would be done. Oh, we forgot to add the negative sign. Oh, I see. We want to remove this one too, so we get the zeros after. And this should give us 0, 0. Yeah, so now we just need to substring the string. And I think there's a way to do this. We could say let bound first this would be kind of very ghetto. We'll say successful division start at false, and then we'll say the first time if digit is greater than 0, we'd say successful division is equal to true. And then we'd only ever do stir plus equal digit if successful division was true. And we still have to add the negative, but Oh. In the final case, if num equals 0, we'll just return 0. The successful division thing is kind of ghetto, but you have to go from the highest starting bit, or otherwise it gets pretty hairy going from the other end. What we could do is also a different version. We'll say let MSB equals -1. And we can just always let these things happen. And we'll say MSB, if they're just greater than 0 and MSB equals -1, which means it hasn't been set yet, we'll set MSB equal to I. And then we can just say stir equals stir.substring MSB going to stir.length. I think this is better. Yeah, so no successful division stuff. That was kind of weird. The number's in base 10. So maybe it's, if we have another problem like this, as long as it's in base 10, maybe we can take it to, actually, no, I think we just need to get it into its value form. Base 10 is kind of the default value form, maybe. So if we had base 16, we could turn it to base 10 first and just see how many times it goes in to see how many times the highest powers of the base we're trying to convert to can go into it. I would say this is constant time since it's just 12 operations. Interesting. So now we have like 12 minutes left. You're given an integer array score of size n, where score sub I is the score of the ith athlete in a competition, which means that there are score.length athletes. All the scores are guaranteed to be unique. The athletes are placed based on their scores. First place athlete has the highest score. The second place athlete has the second highest score, and so on. Placement of each athlete determines their rank. The first place athlete's rank is gold medal. Second place athlete's rank is silver medal. Third is bronze medal. For the fourth place to the nth place athlete, their rank is their placement number. Turn an array answer of size n where answer supplies the rank of the ith athlete. Maybe this one is too simple, but I can't tell if I'm trolling or not. I forgot to change this to 2. My bad. Wait, huh? 10, 3, 8, 9, 4. Placements are... Oh, they don't want us to... Ah, I see. That was unclear from the first example. Wait. I'm actually confused. The first place athlete has the high... Oh, these are based on the scores. And then, so they want 10, 9, and 8. I see. I see. Okay, that's not too bad. So what we'll do is, first we'll map to the place. Well, the place is not really anything. First we'll just map the place and the index that they're actually at before we mess up the array. And so we say place comma I. Then we could just sort A and B based off A, and it's by score, so we do descending minus A sub 0. Since we're doing B sub 0 minus A sub 0, I think we can return the same and we'll say that the output is equal to score dot map change all of these to output. And then the 0, 1, and 2 here will change to places sub 0, sub 1, and places sub 1, and then places sub 2, sub 1. We still have to make sure, because there'd be cases where we don't have at least 3 competitors. So I have to fix that afterwards. Wait, I think I'm getting confused. The athletes are placed based on their scores, where the first place athlete has the highest score. Second highest score. Turn an array answer of size n, where answers of I is the rank of the ith athlete. So we have 5, 4, 3, 2, 1. The output is gold medal, silver medal, bronze medal, 4, 5. Why is 4 and 5 at the end if they have the highest scores? Placements are first. Oh, they want to have the places afterwards. They don't want the scores. This first example was confusing because their places and their scores are actually the same. I get it now. So what we actually can do is say I, and we'll actually just do I dot toString. Oh, not. We actually want this to be places. Then there's maybe they don't care. I think I'm just confused on what the problem is asking for. Because when I print output, maybe my brain is just turned to mush. Oh, we have to add one to it. I forgot. Right, what they do, okay. Output has to retain, so we have to say I just feel, I think my brain is just mush. It's like 2 hours, the hour earlier. I mean, the 45 minutes of review earlier, and then the hour of LeetCode so far. I think my brain is actually fried because this problem is not difficult, but I can tell when I stop actually thinking, I'm just like trying to spit out a solution without actually thinking, which is making this more cumbersome than it is. So I think we're going to stop there.